Good morning, class. Let us solve one problem with infinite line charge. We considered the infinite line charge problem earlier, right? We are going to revisit the same problem and learn how to use the cylindrical coordinate systems. This is sometimes called as circular cylindrical coordinates. It does not really matter, okay? I have again a uniform line charge of line charge density rho, as you can see in the slide. Here I have an infinite line charge in the z-axis, according to the z-axis, okay? And let's say the density of charge present here is rho L, okay? The density of charge is rho L. Which is along the z-axis, going all the way from positive infinity to negative infinity. I again consider a line segment at a height of z bar from the z equal to 0 plane, starting from the horizontal plane, okay? And I consider a small segment dz dash. So this is basically dz bar. I mean z bar, okay, along the z axis from this horizontal plane, okay, from this horizontal plane in this direction. And I took a small segment which is of length dz bar. So the density here should be, the density of charge here should be this dz bar times rho L. So that amount of charge will be present there. Now I have to find out the field at any point in the plane, which I am now going to consider any general r phi and z point, okay? So if I want to find out the field at any point in the plane, let's say this is the point I took. This is any point in this axis, and this point is denoted as r phi comma z, r comma phi comma z, okay? I am not looking for z equal to 0, because if I put z equal to 0, that 0 length, the calculation could be done considering z equal to 0, but the equation will be complex for you to understand, which is why I am taking a value of z. Let me consider any z value and see what happens. You will see that the problem does not become complicated at all. So what is the unit vector for this one? Okay. What is the unit vector for the field point, and what is the unit vector of the source point? So you can easily find it from there. The vector for the source point is r dash. So your source is the line, right? This will be your source. So the vector along this direction is z bar, okay, z prime. Let's say as this is z prime, this is r prime. So the unit vector should be this z prime times the unit vector of z along the z axis. So it will give this, okay. This is at a height of unit vector z. And what is the vector for the field point? It turns out that the vector for the field point has no phi component, okay. So it has no phi component. Again, remember, just because there is no phi component, it does not mean that phi itself is 0, okay. So I have this as r vector plus z vector. So basically, this is your r dash, this r dash, the length of this line times the unit vector will give you the vector in this direction, okay. And what will be the field vector? Let's say your field vector is r bar, which is equal to r into unit vector of r plus z into unit vector of z. As the coordinate of field vector is r, phi and z, let's say this phi is not here. It does not mean that the phi is equal to 0, okay. Phi, there is some value of phi, but the phi component is not present along this vector, okay. But the vector of this field will be r bar is equal to r times r bar plus z times z bar, this one, okay. So what is this vector now from the source to the field point? So what will be the vector? How will you calculate this vector over here? From this source point to this field point, what should be the vector? This one. So this is nothing but addition of these two vectors. R bar is this vector, and this is the vector along the z direction, which is r prime. So r bar minus r prime will give you this vector, okay. So if you subtract them, the equation is something like this. Now we use the expression for electric field. We integrate in the appropriate dimensions. I am looking at the electric field at a particular point r, phi, z in the plane, right? This will be equal to phi L divided by 4 pi epsilon naught. I am going to take this constant anyway outside, okay. So you know the electric field equation that we have used before. So the constant part I am taking outside and integrating the rest of it from minus infinity to infinity. Inside we have r minus r prime, which will be divided by the magnitude of r prime cube. So the equation becomes this. So the equation becomes this. You have to put this over here, and you have to take the cube root of this value. Okay? So r bar minus r bar prime is this one. Okay? So this is written here. As this is equal to this, we put this here. And we have to take a mod, but we have to take a cube root of this value, which is this one, 3 by 2. So if I can show you the electric field equation which we have used before, it will be much easier. Let me find it out, okay? If you can remember this, electric field is equal to Q into the vector divided by 4 pi epsilon naught r minus r bar prime mod whole cube, right? So basically we are taking the constant part outside the integral, as we are integrating this from minus infinity to plus infinity. We are taking this constant part outside, and we are integrating r bar minus r bar prime divided by mod of r bar minus r bar prime whole cube. So if you take the integration, your equation becomes something like this one. So r bar minus r bar prime is equal to this. You put this over here. Okay? The constant part is outside. Then we integrate with respect to dz prime. So if you integrate, your equation becomes rho L times unit vector of r divided by 2 pi epsilon naught r. So using this formula, you can easily calculate the electric field in the cylindrical coordinate. Okay? So let's go to lecture 10. We have completed lecture 9 till so far. Let's try out lecture 10. So let me introduce you to this concept. So I am looking at a new concept called potential. Well, since we are still dealing with electrostatic cases, I am looking at electrostatic potentials, okay? This electrostatic potential is sometimes denoted by phi or sometimes denoted by voltage V, okay? I will use V for now, but sometime later I might switch to phi, okay? It does not matter which one you use, both terms are equally used in literature. So if I want to define electrostatic potential, let me first talk about the point charge. So back to the point charge over here, we know how to calculate its electric field. So there is an electric field out there, okay? Now I choose a particular interesting electric field pattern, right? Let's say I do not want to choose the point charge. I choose a particularly interesting electric field which I somehow have generated, in which the electric field is pointing horizontally. So let's say the electric fields are basically pointing horizontally, okay? And it is all uniform along this particular direction. So the electric fields are all uniform. That is what we assume at this moment. There is no decrease in the magnitude, okay? Now consider, as you know, if I take a point charge, if I take a point charge, if you move along this, the electric field here should be more, and electric field here, the strength should be less. But I am considering this as a uniform electric field. The strength does not decrease. This is my assumption. Now consider 2 points here. Consider a point R2, consider a point R1, okay? I have considered a point here R2 and a point R1 over here. So what is the difference between the charges over here? Let me say it's del Q. The difference between these two charges is del Q. I am taking a test charge del Q, right? And I am going to move this test charge from R2 to R1. So if I want to move the charge at R2 to R1, what will happen? That my electric field is uniform over here, right? So which means its magnitude is not changing and its direction is always along the horizontal to the right. Okay? So I am moving from R2 to R1. Now I know that if I do not move it, right, if I just keep the test charge at the position R2, since the electric field is directed to the right, the charge would have simply accelerated to the right. Because if I have a test charge del q, okay, there will be force acting on this, and the force will be E times del q, correct? So, instead of moving the charge from R2, if I put it here, and this electric field, as I know, uniform, and it is applying a force in this direction, even if I put the charge over here, it will experience a force and move to the right. Okay? And the electric field should be equal to del q times, the charge should be equal to the electric field times del q. What I would have to do is I have to perform some work. Which way I am performing the work? I am actually moving the charge from against the field. So basically I am moving R2, the charge from R2 to R1. So I am applying a force against the electric field, right? Against the force of electric field. So I am moving in the negative direction to the left. So I have to expand some energy. I have to perform some work in order to move the point, right? How much work should I perform? Work done must be equal to the force that I apply times the distance I move. So this is again from the mechanical concept of moving a block. I move it a distance of d, and I apply a force F, then work done will be force time distance. So, in a mechanical point of view, if there is a block present over here and you want to move it, you have to apply some force, and the distance it moves, if you multiply that, you will get your work done. So force times distance will give you the energy. So what is the force in terms of that charge? So the electric field is the force that I am applying. Basically this electric field times the charge will give me the force. But as you know, I am moving it from R2 to minus R1, it should be negative. So basically I am moving the charge from R2 to R1. So I am moving against the direction of the electric field. So what will be the work done in this case? This electric field times charge times the distance moved, and the distance moved is R2 minus R1. So this is the distance moved, okay, and this work done will be negative as I am moving against the electric field. So that potential will be equal to minus E times del R. So if I consider R2 minus R1 as del R, then V should be equal to minus E times del R. Okay? Basically work done is equal to the potential. So potential is equal to minus E times del R. Now what significance is the potential? You remember from your mechanics courses that potential, for example, you have an object which is lying at sea level, okay? Object, let's say this is the sea level, you have an object here and you have a huge mountain over here. From this sea level to this, if you move the object over here, you will gain some potential energy. And if this object is dropped, this potential energy will convert to kinetic energy into mass times velocity, right? So basically the energy is converting to some other form when it falls. So the unit conversion is shown over here. Work divided by charge is equal to volts. Okay? Work is in joules, and we know that voltage is equal to E times del R. So del R is in meter. So your electric field should be joule per, charge is coulomb, okay? Joule per coulomb meter, okay? So joule per coulomb is known as volts. So basically the electric field can be written as volt per meter. If you recall, we had a uniform electric field in a given region of space, right? This electric field over a small distance, at least we can consider it to be constant. For a small distance, let us consider the electric field to be constant. Let the electric field will be directed along the horizontal to the right side. So let this electric field be constant at every point, and it is moving to the right side, okay? And then I pick 2 points over here, call these points as R2 and R1. This is R2 and this is R1, and the difference between these 2 points is del R. Then I will define, or I will find out what is the amount of work that is required to move a charged particle from a test charge from point R2 to R1. So I will find how much work is done for a charge to move from R2 to R1. Please note that this moment, this movement is against the electric field, and we will take this against the electric field into account when we write down the expression for the work done on the charge. So, work done on the charge is the force that we are applying times the distance that we are moving. So, if I call the distance as del r, and del r from this figure can be easily seen to be between R2 minus R1. Okay. So, when I move a distance of del r along the particular path against the field, I will be performing some work. But I know that the force on the test charge is also given by the electric field at the particular point, and we are assuming the electric field is constant. So, we move along from R2 to R1. Okay. So, what we actually get is not exactly, well, though this is work done. If we divide this work done from the test charge, that is to say, if you calculate what is the work per unit charge or work per test charge, that will give me the potential. So, work done divided by the charge will basically give me the potential difference. Although here we have shown that this is the work done, one should actually think of this as differential amount of work done. That is the exact amount of work that we need to do in order to move the charge from R2 to R1, assuming that the charge is already moved from some point to R2. So, in essence, what we are getting from the equation is not the absolute potential, but the potential difference between R2 to R1. Okay. So, with reference to some zero potential, this quantity that we have just written down is actually the potential difference between the points R2 and R1. So, you have del V is equal to minus E times del R. Because I assume that direction of movement is along a certain r direction. And what is the potential difference here? It is the potential difference between the point R1 and R2, which is equal to minus E times del R. Now, there is no rule or there is no requirement that I should always move along the line that is parallel to the electric field. Okay. Sometimes I might choose a path in which the electric field would be making an angle with respect to the path along which I am moving charge. So it does not mean that the electric field will be only in this direction. It could be along this way as well. Okay. So what happens here, we can take the projection to this horizontal path. So if I take the projection, if this is x, so f dot x, I will get a projection here. So the vector along this direction should be unit vector x bar. So f times this x into x bar will give me the vector along this. Okay. So if del x tends to 0, so we can replace this del x by dx, and if we integrate that, we get the work done. This work done equation can be written in terms of voltage as well. So dV is equal to minus E times dL. So now if we can now write down saying that the voltage difference or the voltage amount of the voltage between the 2 points, if I move a distance along dx, is actually given by minus E dot dl. Okay. And what is this dl? If you remember the coordinate system that we talked about, dl was the line element. So it is actually the vector in which gives us direction of movement. So if I move in an arbitrary path, then that arbitrary movement can be characterized by a line segment, which is a line vector segment, which is dl. Okay. So now if I pick 2 points B and let us say I am moving the charge from point B in the space to another point A in the same space, in the space. Okay. So I am picking up particular path over here. The path, the total potential difference between the 2 points, or the potential difference between the 2 points A and B, will be obtained by integrating this expression dV is equal to minus E dot dl over this entire path. So if the path is given a name called C, then the potential difference between these two paths, namely V at a minus V, so this dV can be written as this: V of A minus V of B equal to minus integration of E dot dl, and it should be from B to A. So what is E and what is dl? dl is the vector element, line element, okay, here. And then electric field is the electric field of the region of space in which we are moving the charge. So this expression is very crucial for you to note. The potential difference between the 2 points is given by the line integral of the electric field, which is a vector quantity along the particular direction. So note that both the electric field as well as the line segment both are vectors. So you need to specify the direction of path as well as you need to specify the corresponding values of the electric field at each point in the path that you are taking, okay. Now there are certain very easy consequences that we can find out. One of the things that has happened over here is that the left hand side is actually a scalar. And for the electrostatic field that we are considering, this line integral or path integral is completely independent of the path that you have chosen, and it depends only on the endpoints of the path, okay. For example, if I take one path from point B to point A, say I go straight up along the path, and then the potential difference will be some del V. This del V is V A minus V B. So this is same potential that you are going to get. If you follow the path number 1, which is a straight line path from B to A, suppose you do not go straight from B to A, let's say you go from B to some other point C, and from C you head to point A. Of course, you are still going the same final point, but you are now taking a different path. So now let's call this as path 2. What I mean is, instead of going from here to here, you can take the path from this point to this point, then this point to this point, and this point to this point. Irrespective of the paths, your voltage difference at these 2 points will remain the same. Even if you take the path from here to here, your voltage will remain same. Even if you take the path from this point to this point, this point to this point, and this point to this point, your voltage will remain the same, even if you take different paths. It will only be dependent on the endpoint, initial and the end point, or the final point of the path, okay. And the third and very important observation is that if you move in a closed path, you start from a point, you move around and you come back to the same point, the potential difference will be 0. But in terms of the line integral, that closed line integral will actually be equal to 0. Any such field that would satisfy this criteria is called a conservative field. With this, now let us go to the point charge that we left off slightly earlier, okay? Have a point charge. So there is a point charge Q here. And the electric field for the point charge, that we have not actually calculated the electric field. We have calculated electric field for line charge, but we did not calculate the electric field for a point charge. But we know how to calculate the electric field for a point charge, okay? So this is the point charge. So for a point charge, we haven't calculated the electric field, but we know how to calculate the electric field of a point charge. Because if I place any test charge over here, there is my test charge. So if I place a test charge over here, we can calculate the electric field of a point charge. And the force on the point charge will be equal to Q, and let us call this as small q, small q. So capital Q times small q divided by 4 pi epsilon naught, and the charge is kept in air or free space r squared, which is the length or the separation between the source charge and the test charge, and it will be in the direction that joins the two lines or joins the two charges. So basically your electric field should be capital Q times small q divided by 4 pi epsilon naught times the distance between these two charge, which is r square, and the vector along this r should be the unit vector r bar. So this is how you calculate the electric field over here. So basically this was the force. So if you divide this force by Q, you will get the electric field, okay? And this R is basically r bar minus r bar prime. Okay. So from here we can calculate the electric field of a point charge. So let us end the lecture here today. We will learn about spherical coordinates and potential, more about potential in the next class. Let us end the lecture here today.